In our discussion of computation, we take a rather loose approach to the notion of computation. I haven't described Turing machine, which is usually considered as a model for computation. So most computer scientists would study computations on the basis of this particular model of computation. Neither did I talk about uniform family of circuits, which is another approach to computation. That's fine. I just want you to have some intuition and think about computation as operations on symbols. And of course, those symbols can have certain meaning, and there could be an underlying mathematical structure behind those symbols. But all our operations will be essentially on binary strings. So when I write a cat with x in it, and then I write that x is a binary string, so a sequence of zeros and ones of length n. So it really means that it's represented as a n-fold tensor product. So think about it as x1 tensor x2 tensor all the way to xn, where x1, x2, and so on are either zeros or ones. So we are having a vector from a computational basis, and I'm having n qubits, and they can represent binary strings of length n, and then I'm just when I compute, I perform operations on those binary strings. Now, of course, I can view also those binary strings as representing something. So when they represent themselves like binary strings, so say 1 0 0 1. So if you think about a binary string as a binary string, and then you think, what kind of operations I do on binary strings? Yeah, well, you can do, for example, addition bit by bit. So so the thing that we did for the one-time pad. So you may think that the underlying mathematical structure behind binary strings of length n is a group which we call Z2n. So where you can add binary strings, so they form a group. You can also think about them as binary vectors. So you can think that they form a vector space, n-dimensional vector space over the Galois field, binary Galois field, right? So the entries are either 0 or 1, because you can think about these operations on individual bits either as something that forms group Z2, it could be a Galois field F2. When you have n qubits, you can play with binary strings, and as I said, you can think about them as binary vectors. So for example, if you have two binary strings, x and y, you can define the scalar product of the two, and you would define it as that would be x1 times x1, x2 times y2 plus all the way to xn, yn. That's a way to define a scalar product if you start thinking about your binary strings in terms of binary vectors. Then again, you may think about your binary string representing something else. For example, x may represent a number in binary notation. So in this case, you may think about this as number 9, right? So that would be so it's just number 9 written in binary. And then you can think about operations on integers. So for example, you may think that the underlying structure that you are interested in is a group Zn, where n is usually, if you have n qubits, that would be n would be 2 to the power small n. So that's a group of integers that you can do addition modulo n on them. So that's a group. You can, of course, you can find some other interesting groups. So for example, this one. So that's the group with all the integers which are co-prime with n, and the group operation is a multiplications modulo n. So yeah, what I'm saying essentially is that, you know, we operate on the binary strings, but behind binary strings, that you know, it's up to you what kind of meaning you are going to give to this binary string. Is it going to be just 1 0 0 1, or is it going to be number 9, or is it going to be something else, perhaps a binary vector, or perhaps some other objects that you have in mind. So it could be algebraic structure behind your interpretations of those binary strings. It's usually a group structure. So in fact, we just only play with those two groups. Either this one and this one will appear. This may appear in the studies of factoring, but the two groups here that are the most common that we often play with. But whatever we do in terms of operations on binary numbers, on bits, on zeros and ones. So in fact, what we are doing is we are evaluating, when we compute, we are evaluating Boolean functions. So in general, it would be a function of the type, a function that maps strings of binary numbers of length n into binary strings of length m. In fact, you can, instead of looking at this class of functions, we are okay if we just analyze all Boolean functions of this type, because any function of this type can be seen, in fact, as m Boolean functions of this type, right? So, for example, the first Boolean function will just evaluate the first bit of this mth, the binary string of length m. The second Boolean function will evaluate the second bit, and the mth Boolean function will evaluate the mth bit. So in fact, we don't lose anything in terms of a general approach to the subject if we just look at Boolean functions of this type. And so now we know, I hope you know, that any Boolean function of this type can be constructed, or evaluation of any Boolean function of that type can be constructed using very simple primitives, so using logical operations such as logical not, logical and, logical or, and some others. But for example, if you pick up not, logical not, and logical and, you are done. You can just construct anything using only the two logic gates of that type. Now, the one problem we may have with this is, of course, that logical not is a nice reversible operation. It's very simple to implement. But if you look at logical and, it's not a reversible operation, right? So if you look at the output of AND gate and say it is 0, so you don't know really whether input was 0 0, 0 1, 1 0, any of the three could be there. So we have a little bit of an issue how to implement a logical AND as a reversible operation, because if we want to implement it as a unitary, it has to be reversible. In fact, the whole thing about reversible computation predates quantum computing. People pretty early started asking questions, how much energy does it take to compute? And then this kind of line of thinking took them to looking at the thermodynamics of computation, and then they figured out that what really costs energy is losing information in the process of computation. So for example, if you have logical AND, you lose something, right? You lose information about your input when you progress through logical AND. You do useful computation, but somehow you cannot just go backwards. So it's irreversible operation. And that actually costs you energy. So then the question was, okay, well, if we do things in a reversible way, if we can, and the answer is yes, we can, do we have to then pump energy into the computer to keep it going? So the answer was, well, you know, if you do it in a reversible way, you don't have to. But there are some other issues. I'm not going to go into this, but just to say that there's a whole body of knowledge how to construct computation in a reversible way. And so let me just give you an example of one logic gate that's been extremely useful for constructing circuits in reversible computation. And in fact, it is a universal gate for a reversible computation. So it's called Toffoli gate, named after Tom Toffoli. I hope he has two F's. Tom, is a very cheerful and very interesting computer scientist at the time from MIT, I guess, and now moved to Boston University. A wonderful character. Anyway, Tom came up with this gate which operates on 3 bits. And you can call it controlled not. So I have the first 2 are controlled bits, and the third one is the target. So let me just label input as x1, x2, and let the target be, let the input for the target one will be y. So the Toffoli gate acts as follows. If the 2 top qubits or bits are in 1, then you just flip the target bit, the third one. But for any other combination, you don't do anything. So if it is 0, 0, 0, 1, and 1, 0, you just leave the third bit as it is. So the x1 survives, x2 survives. And the third one, let's write it this way. So it's y plus, it's binary addition, x1 and x2. So if x1 and x2 are, I guess I can write it as x1 times x2, or some of you may prefer this notation, x1, x2. So if the 2 values of x1 and x2 are both equal to 1, then you add this 1 to the existing value in the register modulo 2, so it's binary addition. So in other words, you just perform operation not on the third register or the third bit. Now, so it's possible to show that this one gate is universal for all reversible kind of computations, and you can also quantize this gate in a sense that yeah, let me just quantize it by putting cats here on those labels here. That means it is a good reversible gate, and one can just have a unitary transformation that does the job. So it's not so difficult actually to construct, and you can figure out for yourself, you know, what is the corresponding matrix for this operation. But you can also see why there is a good reason for this to be universal. If you can see, for example, that if you set x1 and x2 both equal to 1, then this gate essentially performs a not operation on the third bit. And if you want to perform logical operation not on x1 and x2, you set this one to 0, and then you have at the output on the third qubit, you have the value of x1 and x2. So you can do not, right? You can do and that's good enough to construct any Boolean function if you can, if you allow some fixed inputs to your Toffoli gates, and you can just combine them into a circuit. So you can evaluate essentially any Boolean function using this gate. It shows you actually something very interesting. In order to, something that we are going to use in more general setting for quantum function evaluation, in order to construct a reversible operation representing irreversible logical operations, so like a logical AND, we keep the inputs, right? So we keep x1 and x2, and we just place the result x1 and x2 in some other bit or some other register, some other sequence of bits. So that will we will use this for in general for as a sort of a construct, because we may be just trying to implement Boolean functions, which obviously are not reversible, because you map a binary string of length n into 0 and 1. You have 1, and that could be just many binary strings that actually that have the value of this function up on those strings is equal to 1. So the the construction of quantum function evaluation will be very similar, will be actually pretty much identical to what we have for the AND gate. We will have our input register where we'll just store the value x1, x2, x3 all the way to the xn. And those values will survive, so the cats in those states will appear at the output after the function evaluations in the corresponding qubits in the first register. So that's 2, 3, xn. And this function evaluation will just simply add the value of the function to the second register, which stores the value of the function. So that's kind of, you know, few remarks and comments upon the notation, the labeling, how we evaluate irreversible logic, classical logic gates in a reversible way. A few words about reversible computation that predates quantum computation, and you know, we were actually in the early days of quantum computation when we were working on quantum circuits for some simple function evaluations. We're actually very grateful to all those guys working on reversible computations earlier, so that we could literally pick up those circuits and just quantize them, by meaning just implement them by simple unitary operation. So that was a good thing. There's a bit more to it, but this is what I guess it is just what you should know for the purpose of this course.